Okay, let's get started. It's a little early, but thank you for coming to Dr. Thesis defense by Jacob Guggenheim. I'm Harry Asada, his advisor. Usually, an advisor, introducing the students. If students are very nervous, the advisor have to say some kind of joke. But today, I don't think I have to say any joke. Jacob is always relaxing, having a nice smile, so I don't have to do that. Jacob is very much multi-talented student, very supernumerary talent he has. His master thesis was in very different areas. That was on the cell biology, and he had pretty good solid publications published in the high-impact science journals and on spheroids. And moving up to doctoral studies, I recommended him to do something different, and I recommended him to work on the supernumerary robotic limbs. And by that time, some brain and cognitive scientists started publishing some work on the effect of superlimbs, supernumerary limbs. What happens when you attach the foreign object, this robotic system, to your body? Does your brain really support that? Does your brain really control both natural limbs and robotic limbs at the same time? Lots of questions, very fundamental levels coming out. So some people start working on that. So why not? We should actually focus on some of the fundamental human issues along with the robotic system design. So that's actually how Jacob started this work, supernumerary robotic limbs. And in fact, in dealing with the human data, the student have to do lots of statistics. And Jacob is one of two students in my group who can do statistics very well. So ever since he has been working so hard, both doing the engineering jobs and something beyond the engineering, bio areas. And this may be a good mixture of the two. So you hear more about it. Jacob?
Cool, thank you. So I'm Jacob. I'm going to talk to you today. Well, thank you for all for being here. I really appreciate it. I'm going to talk to you today about the contributions of the human operator to supernumerary robotic limbs. I'd like to make a quick note first. I'm going to refer to them as either superlimbs or SRLs. We've been referring to them as SRLs for a long time. We've recently changed the terminology to superlimb. I might slip up and say SRL. They're the same thing. Cool. So I'd like to begin with a slide from actually a previous grad student's thesis, defense. So back in 2015, Federico Perietti was a graduate student with Professor Asada, and he showed this slide in his thesis defense. And he basically used this to propose the kind of different areas that these SRLs or superlimbs could be applied to. And so he proposed these kind of varied areas, for example, elderly assistance, rehabilitation, all the way to like heavy industry manufacturing and even domestic uses. And kind of a hallmark of a lot of these applications is that fundamentally the superlimb is performing some sort of secondary supportive task while the person performs some sort of primary task. And so this is, to Professor Asada's point, the multitasking we were referring to earlier. And over the years, our lab has kind of tackled a lot of these problems. So in 2015, Federico built a superlimb that he mounted on the waist, and they used this to kind of increase the size of the support polygon so that people could balance better while they were walking. In 2015 as well, Baldwin, another grad student within our lab, developed a superlimb that sat on the shoulder, and the purpose of this was essentially to hold like a ceiling panel in place so that you could remove your own hands and install it. In 2016, Fei Wu built basically an SR finger, so a superlimb mounted on the forearm that allowed somebody who previously would require two hands to perform some sort of task could now perform that same task with one hand. And this is really important. This is kind of a large area because 1 out of 6 Americans suffer from some sort of limb mobility or dexterity problem. And so that kind of gives you the scope of the problem that this particular superlimb was designed to address. And then finally in 2017, Dan Carrick built what we call the mantis bot. The mantis bot is a superlimb mounted on the back, and this was basically designed to allow somebody to kind of free up their arms for near ground work. So if they were in heavy manufacturing and they were trying to weld, the superlimb would support them near ground and they could freely weld and hold themselves in a more ergonomic posture. And this was designed to address the nearly 240,000 workplace injuries that occurred in manufacturing and agriculture sectors in 2014 alone. So these are big problems, right? These are big problems that we're trying to address, and it's kind of worth, I guess the point of this slide is to suggest to you that it's worth pursuing these problems and pursuing the advancement of superlimbs. And so kind of not surprisingly, other groups have followed suit. And so I've highlighted a few of my favorites here. The thing I want to mostly talk about with these is that they're mostly focused on increasing the design or improving the design of superlimbs or improving the application of superlimbs. So on the top left, we have a 3D printed superlimb by Carter Davies et al. Essentially, this is designed to be a cheap 3D printed superlimb. Bottom left, they use soft robotic superlimbs. Top right is actually my personal favorite. It's a tail, and that's used for basically balance augmentation. And so all of these, again, are mostly focusing on improving the design. They're mostly focused on different applications. And as Professor Asado alluded to, it's both within the kind of work outside of our group and the work inside of our group. We haven't really been focusing on the contributions of the human operator. And so the question is, do we actually need to? Why should we focus on the human operator? And I'm going to tell you a little story from a neighboring field that kind of motivate this. So passive exoskeletons, they're basically like a wearable robotic system, and the desire of these systems is that they reduce the metabolic cost of walking. And so back in 2003, a group led by an author, Vanden Bogart, essentially proposed a design for this passive exoskeleton. He called it an exotendon, and based upon a number of pulleys and other kind of mechanical elements in it, they found that their simulations showed they would reduce the joint moment required for walking by up to 71%. And so naturally, the community was very excited about this. You would assume that if you could reduce the joint moment required for walking, you would in turn reduce the metabolic cost for walking. In 2011, it was finally actually built by Van Dyke et al. And kind of anticlimactically, they found that the energy expenditure while walking with the exoskeleton actually increased. And they hypothesized that this was kind of two factors. They hypothesized first that the fact that the person actually had to carry around the mass of the frame was contributing to the increase in metabolic cost. But also they highlighted, and for our purposes in particular, it's important that their human users had difficulty in controlling the exoskeleton. Finally, in 2015, Collins came around, built a exoskeleton that, despite delivering no positive mechanical work, successfully reduced the metabolic cost of walking by 7.2%. And so the story arc here is, didn't focus on the human operator, didn't really understand how it was going to interact with the human, surprising failure, focused on the human operator, success. Excellent. So kind of from our perspective, then, we're going to try to do a similar thing. We're going to look at the contributions of the human operator to superlimbs, and we're going to do that in two specific areas. The first area is with the design and communication of two superlimbs, and then the second area is kind of the feedback from superlimbs. And so we're going to jump right in with the first half of this presentation, which is going to be on the design of and communication with superlimbs. Generally, the idea here is that because the superlimb is mounted on a person, the person can actually move around and kind of move. The person can basically help the superlimb perform a task because we have all these high redundant degrees of freedom. And so, again, turning to Federico Periotti's defense, we see here is another slide from his defense where he basically showed the reduction in weight over time of his SRL or superlimb prototypes. And this is really important because this is a wearable system. If it's a wearable system, you want it to be comfortable, and to be comfortable, it needs to be light enough that you're comfortable wearing it for an extended period of time. And so you can see here from the peak, he had a superlimb prototype that was roughly 30 kilos. He was able to reduce that to just under 5 kilos over several design iterations. And the way he achieved this was by kind of using different materials or lighter weight actuators or smarter actuators. And this is great, but we kind of wanted to ask a different question. Can we, instead of just kind of taking advantage of better materials or actuators, can we actually just simply remove actuators? Because they're a primary component that contributes to the weight of the superlimb. Can we just remove actuators? And can we do this by taking advantage of the fact that this is a wearable system? So our goal here is to leverage the high degrees of freedom of the human body to split the motion space such that the superlimb only has active degrees of freedom for those degrees of freedom the human cannot provide. And we're going to do this in 3 steps. The first step is we're going to do an analysis of some sort of task that we've chosen, and that's going to determine the required degrees of freedom as well as the placement of the superlimb on the human body. The second step, is we're going to quantify the usable human body movements, and then finally we're going to use this quantification to determine how we can split this motion space. Just to kind of ground our demonstration of this methodology, I'm going to present it on this particular task. And the task I've chosen is having a superlimb essentially open a door for you, and specifically open a door while your hands are full. The reason we've chosen this task is kind of twofold. First, it's kind of a well-known task in robotics. You see a lot of Boston Dynamics videos of robots opening doors. Secondly, it's a very relatable task. We've all been there with like 2 grocery bags. We're approaching our door and we're like, crap, if I only had a third arm to just grab that door, it would be fantastic. So this is essentially a very relatable scenario for everybody. And so if we look at the required degrees of freedom that would be needed to perform this task just from a robotic perspective, we need to first position the end effector, which is essentially a gripper, in X, Y, and Z. We then need to grab and rotate the door handle, so that's 2 additional degrees of freedom, gripper and roll. We need to open the door, which is movement in X and Y, and then finally we need to release the door, which is a gripper. So in total, these are 5 kind of degrees of freedom that would be required, active degrees of freedom would be required to perform this task. We're also going to use this task to help us determine where to place the superlimb. It's fairly common in superlimbs to use the task to determine where it gets placed on the human body. Generally, they follow kind of 2 rules. First, you want to place the superlimb kind of close to where the eventual task is taking place. So for example, with Baldwin's work, he's going to be working on the ceiling, so it makes sense to mount those on the shoulder as opposed to like the shin or something. The second thing is that you want whatever the base you choose to be stable enough to kind of deal with the forces that are being provided. So you want a kind of larger body area to mount these onto. Based upon this, we obviously don't need to choose the waist, but we can choose the waist for our task because door handles are roughly at waist height, and that's a big bulky area that can support a lot of weight. So we've chosen in this particular case to mount the superlimb on the waist. The next step in this methodology is to quantify the usable human degrees of freedom, and that's given the constraints of the task. And the reason we're going to do this empirically as opposed to with models is because there do exist models of human body motion, but they often become less accurate as you add constraints and increase in complexity. So instead, we're simply going to empirically measure the kind of degrees of freedom the human can provide. And we're going to do this with a motion capture system, so that is me on the left, wearing this motion capture system, and on the right you can see that's a rendering of me exploring the degrees of freedom, so essentially I'm just rotating about my pelvis in the 3 rotational axes. Excellent. This is that data. So you can see here that we have rotation in pitch, roll, and yaw. If you remember back to the like analysis of the task, the 5 required degrees of freedom were X, Y, Z, roll, and gripper. So what we're really concerned about here is roll. And you can see that with roll, we actually only get roughly plus or minus 20 degrees of rotation. That's not sufficient to open a door, and so therefore we can conclude from this that the human cannot provide sufficient roll to help open a door. However, rotation about the pelvis also results in a translation at the end effector. So if I'm standing here and I rotate, the end effector, which is here, will move. And so we also want to understand the effect of the rotation of the pelvis on the translation of the end effector. And we can do this with the transformation matrix. So seen here, and we basically calculate it, and it's represented by this kind of transparent partial ellipsoid. And so from this analysis, we can see the person can provide roughly 90 centimeters of travel in X, 70 in Y, and 60 in Z. So that's actually a fairly significant amount of travel in these 3 translational degrees of freedom. Finally, we're going to split the motion space based upon this analysis. So once again, going back, we required 5 degrees of freedom, X, Y, Z, roll, and gripper. The human can supply X and Y, both because they can rotate to translate the end effector, but also because you can literally just walk around. The human can provide some Z. We did say some Z simply because it's not comfortable to hold a box for an extended period of time and do like squats. So we don't want the person to do a significant amount of Z. However, the superlimb is only now going to need to provide roll, gripper, and Z. And so the take-home message here is we had this 5-degree of freedom system, 5 active degree of freedom system, and we've successfully reduced it to 3 degrees of freedom. So that's a significant reduction in weight and complexity. So now just to take a look at what this task would look like with this new reduced actuator design. The first step, instead of the superlimb having to move in X, Y, and Z, the person moves in X and Y, and the superlimb moves in Z to position the end effector at the door handle. The superlimb then grabs and twists the door handle. The human backs up, moves in X and Y. And then finally, the superlimb releases the door and the person is able to walk through. So we've designed this system. We've successfully reduced the number of actuators. The next step is to control that system. And once again, we're going to rely on the kind of highly redundant degrees of freedom the human body has to send control inputs to this system. So specifically, if you look at this task, you can see here that while I have to hold a box, if I'm holding a box in this particular task, the total force is kind of set, right? I need to be able to hold this box, I don't want to drop it. But the individual force on each of my fingertips can be varied. And so this variation, this redundancy, is what gives us kind of space, essentially, to send command inputs. And we have 2 kind of criteria for the command inputs we want to generate. We want to make sure they're A, physically achievable, and we want to make sure that they don't look like the primary task. And that essentially means that it's not data you would normally see when you're performing the primary task. And so we're going to do this by basically determining a command input subspace. The first, I'll walk you through this. So that's dark, sorry about that. The red rectangle here represents all of the normal grasps that one could have for this box. And so essentially, you have, if we're measuring the force on your fingers, you have 5 fingers here, 5 fingers here, that's 10 different fingers. All of those would be collapsed, all of those forces would be collapsed into a single data point that exists there. And so that's me just holding the box. And obviously, there are different ways to normally hold a box, and so there's a bunch of different data points all around here. The next space is what we're talking about when we say it doesn't look like the primary task. So you can see here, I can vary the force on my fingers, I can vary the force on my thumb or index finger or whatever. All of those are not something you would normally expect to see if somebody was just normally holding a box. However, we also have data here that would basically doesn't look like the primary task. It certainly doesn't look like the primary task if I drop the box. But the problem with this is what it does is it's physically infeasible. It causes me to fail the task. And so we need to further subdivide this space into physically achievable, which we're going to call R, and the infeasible space N. And what we're seeking is this command input subspace, which we're going to call S, and that's the intersection of R and NT, where NT is the null space, which we'll talk about, of the task. Great. Once again, we're going to use 3 steps. Love those 3-step methodologies. So the first step is going to be take data on the normal task performance, as well as kind of exploring the space. Step 2, we're going to identify the range space, R, of the task. That's that physically achievable stuff. And then finally, we're going to find the intersection of R and NT to get the subspace S. So the first step is to take data. The way we're going to do this is Rachel Hoffman has built this beautiful prototype that basically allows us to measure force on the fingertips. And so it takes force sensing resistors and puts them on the fingertips, communicates that to an Arduino, which then talks to our computer. And we're going to use this to take data. So this is me just kind of normally holding a box. You can see that we can measure that force. So we're looking at the force on all 10 fingertips. We also can vary the force on each fingertip. And what you're seeing here is you're seeing a position varying. The force is also varying on each of those fingertips. And so it's very important to remember we're thinking about force as opposed to position of the fingertips. This is what that data looks like. So in red here is shown the normal holding box data. And each one of those data points represents a vector that's actually six numbers, each number representing one of these 3 fingers, or 6 fingers, that's right. And so essentially it's 6 numbers for the force on each of these 6 fingers. The blue is what was found from the exploring the space. And so that represents what's physically achievable by the person, because in that exploring the space, I didn't drop the box, I didn't say anything really uncomfortable, and so that represents what's exploring the space. However, we don't just want kind of the data within that space. We actually want to know what that space looks like kind of on a broader level. And so the way we're going to do this is we're going to use something called principal component analysis. Principal component analysis basically looks at the variance of this data and gives me vectors that are all orthogonal to each other and span the largest variance. And so we perform principal component analysis, and we get 6 outputs because we had 6 data points for each data. And we can see here that basically the graph on the right here is the amount of variance in that data explained by each principal component. And so you can see here that the first 4 components represent roughly 90, a little over 90% of the variance of the entire data. And so generally what you would do is you would truncate at that point. And so you have 4 eigenvectors, which are derived from the principal components, and they're v1 through v4, and we're going to say that these span the space, the range space R. These are contained within R, which is that physically achievable space. And we're going to just throw out 5 and 6 because those might as well be noise. The next thing we need to do is we need to determine if those vectors that we found in R are also in the NT, which is the null space of the task. So what I neglected to mention earlier, but we'll do so now, is that the natural holding of the box, how you would naturally hold the box, and what NT, RT and NT are actually orthogonal to each other. And so what we can do is we can use the inner product of the data in RT with each of the eigenvectors that we found in the previous slide to determine in which space those eigenvectors lie. And so essentially this is what that looks like. On the x-axis you have each data point, the inner product of which is taken with each eigenvector. So there's 4 eigenvectors there. And we're going to say anything below this line, which is just some threshold we've set, is within the null space of the task. Anything above that line is not, and we're not interested in it. And so from this, we can conclude that vector v2 through v4, eigenvector v2 through v4, are in NT. We also know, because those were directly derived from the range space R, that those are in R, and thus we can say that S, the subspace we've been looking for the entire time, is spanned by the eigenvectors v2 through v4. Excellent. So now we have this subspace. How do we actually use it? So let's say we have some new measurement, f star, and the old data is shown in red. So that was my initial, how I would normally hold the box. You can see here in green, the new data has this kind of area that spans out here. And so that was essentially me trying to send a code. That was me saying, this is not normally data you would see within the normal holding of a box, so I'm going to use this to send a code. What we're going to do to this data is we're going to project it into this command subspace S. We're going to use this projection matrix down here, and we're essentially going to compare it to some manually defined code within that subspace S. And so this, this green arrow here, or green X here, represents that command, that code, manually defined code. And then we're going to take some distance metric, and we're going to say, if you're close enough to this manually defined code, then that is a command being sent. And if it's too far, we're just going to ignore it. And that way we don't accidentally trigger a command to the superlimb when we did not want to. So kind of now to understand what those codes could look like, we have this task where the person is basically having the superlimb open the door for them. We can break this up such that the superlimb has 4 codes to command its actions. So the first code that you would send to the superlimb would tell the superlimb to move up in Z. The second command could be move down in Z. The third command could be grip and rotate the door handle. And then the last command can be let go of the door. And I kind of want to point out here that you could use these codes to send continuous inputs to the superlimb. You could be like, continue moving this direction as I send this code. But here we've chosen to basically define action primitives that are mapped to these codes. And part of the reason we've done this is because it relieves the burden on the person, such that all they have to do is say, do this one thing, and the superlimb will both grab and rotate the door handle with the appropriate timing and everything. So we actually went ahead and implemented this. Just because the force sensors we were using were not the most robust, and for ease of demonstration, we actually ended up basically thresholding the force signal from each finger to a binarized on or off. And then we classified each code by whether it exactly matched the code that we had defined. And so we have the 4 kind of codes we were seeking. We want to move the SRL up, move the SRL down, grip, and let go of the door handle. So this is the system in action. So the subject here first commands the superlimb to go up. She next commands the superlimb to grab and rotate the door handle. She backs up manually, so these are the kind of degrees of freedom she is providing. And then finally, she commands the superlimb to release the door, and then release the door handle as she walks through. Obviously, you see we are tethered here. So we made a better version last night, and I'm going to show this video because it highlights a few things that I want to talk about kind of in addition. This was made by Han Jun in the last month, so that's kind of a monster amount of work to do, but he has done a very good job. So it's kind of the same idea. It's going to open the door handle here. I'm going to take a turn. The other thing I want to highlight is that because these superlimbs are mounted on a person, they're incredibly portable. And so this is one of the advantages of this portability is he can kind of do all the movement of this. He can use it to do what you would normally consider safe options. So for example, instead of sticking his own hand in, he can use the superlimb to do that. He can use the superlimb to press elevator doors, and then he can kind of continue on his way. We took this last night. Excellent. Okay, so on to the second kind of part of this presentation. We've designed the superlimb. We know how to control it, but we still haven't really gotten at the fundamental questions about superlimbs, which are, generally they're designed to do supportive tasks as somebody else does some sort of primary task. And so this is a really good example of this. So Baldwin is going to use the superlimb on the shoulder to kind of hold a plate in place as he goes ahead and screws it in. And you can see here that he's basically relying, a key feature here is that as the superlimb performs these actions, at the base of the limb, he gets these reaction forces. So he feels what the superlimb is doing. He doesn't actually need to visually see what the superlimb is doing. He actually gets feedback, what we're going to call inherent haptic feedback, from the superlimb as it performs these actions. So he performs some sort of primary task, which is like fixing it in place, while the superlimb does this kind of secondary task. Obviously, this inherent haptic feedback is not unique to superlimbs. So prosthetics have often, or a lot of prosthetics will get this same inherent haptic feedback. If I have a prosthetic and I knock it against something, I'm going to feel that reaction force on the residual limb. But I specifically want to talk about these type of Bowden cable harness prosthetics because they also give you force feedback in the gripper, which is kind of rare. And so basically the way these work is that usually as I extend my arm, the gripper will open, and as I pull my arm back, the gripper will close. And I can actually feel the thing I'm gripping based upon the resistance to my arm moving open or closed. And so there was a study done in 2017 that basically found that people with these body-powered prosthetics were able to more accurately identify objects based upon their stiffness as compared to just visual feedback alone. And that's kind of what we would expect. Interestingly though, there was numerous surveys done, this particular one was done in 2016, that kind of looked at people's preference when it comes to different types of prosthetics. So these two shown here are some of the more advanced commercially available prosthetics. They're called myoelectric prosthetics. So they use the basic EMG signals on your that are generated by your muscles to control them. But a critical feature of, to my knowledge, every commercial myoelectric prosthetic is they have no feedback on the force that somebody grips with. And so when they do surveys comparing these really kind of relatively primitive mechanical designs like this Bowden cable harness prosthetic versus these very complex myoelectric prosthetics, they find people still often prefer the Bowden cable kind of body-powered prosthetics because of that force feedback. So that just should kind of give you an idea of the importance of this inherent haptic feedback to people's preferences in using these wearable robotic systems. In Superlimbs, though, kind of different from prosthetics, we're often looking at this multitasking, and so we're going to kind of outline 3 use cases here where we see Superlimbs being useful, or the inherent haptic feedback from Superlimbs being useful. The first case is when vision is occluded. So imagine if instead of like a small box, they had a significantly larger box that was blocking their view. You can imagine that it would be nice to know when the superlimb has made contact with the door handle so that they can initiate that next step, grab the door handle, and twist. Case 2 is when vision is not the appropriate modality for actually sensing that state. So a really good example of this is in standing assistance. If I'm seated and I want help standing up and I want the superlimb to help me stand up, What I really want is the superlimb to apply a force to the ground to help me stand up. And the critical part of this is often the force that I want is going to be different than the force that you want, and the force that I want today is going to be different than the force I want tomorrow. So very often you want to manually control the force output of these superlimbs to help somebody stand up. But it's very difficult to visually assess force output. And so actually haptics is a better modality for sensing force kind of output. Finally, case 3, we have in combination with visual feedback. There have been numerous studies that basically show haptics with visual feedback will often lead to more accurate object grasping or whatever, though usually it will also result in the person having slower response times. We're going to particularly focus on case 1 and case 2 here. We designed this experimental setup to kind of get at this fundamental multitasking aspect of superlimbs. So the person is placed in front of a desk, and the superlimb is actually clamped to the desk. And so the reason for this is because there's then no positional change in the superlimb as it exerts a force on the table. And the result of that is that person cannot visually assess what is happening with the superlimb. They must use the inherent haptic feedback to judge what is happening. They're also placed in front of a monitor, which will basically show some sort of demanding visual task. In this particular case, it's a series of yellow and white letters. They have to press A on an Xbox controller that they're holding every single time they see a white letter. Excellent. They also interact with the superlimb through the same Xbox controller. Just to give you an idea of how the inherent haptic feedback is being delivered here, because the superlimb is clamped to the table, as the motor generates torque, that is reflected both as a force on the table, which we're measuring with this little force sensor, as well as a kind of scaled version of that is reflected to the actual base of the superlimb, which is then delivered to the person. And just for reference, the maximum force felt during these experiments was roughly 45 newtons. We've designed 2 experiments here. The first one is going to kind of be from that standing assistance model, where we're basically going to have the person fully manually control the force output of the superlimb. And we're going to have 3 conditions. We're going to have the vision-only condition, we're going to have the haptic-only condition, and then we're going to have a haptic and vision, and so that's the multitasking condition. The haptic-only task is essentially going to be this. They're going to have some sort of disturbance applied to the superlimb, such that if they took no action, there would be a force buildup on the superlimb. Their job with the Xbox controller, and you can see their command inputs here, is to basically reject that disturbance and keep the force close to 0. And so we're going to measure their performance based upon the root mean square error of the difference between the force measurement in blue and their goal, which is the black dotted line. Cool. So we went ahead and performed this. I think we had 9 subjects, and the first question we want to ask is this performance is the performance on the haptic task better than if they had taken literally no action? And so the way we're going to measure this is we're going to integrate that disturbance, which was in units of force, newtons per second. So if we integrate it, we now have newtons. And you can see here that if over the course of this particular trial, if they had taken no action, what would have happened is the force on that superlimb would have gone all the way down here to minus 270-ish newtons. So that's a fairly large magnitude of force. However, the action they did take with the Xbox controller to reject that disturbance kept the force roughly at 0 throughout the entire trial. Obviously, we want to answer this in a more quantitative method rather than very qualitatively. And so the way we're going to do this is we're going to look at the aggregate data. So this is every single subject's performance. If they have taken no action versus the action they actually did take in the blue line. And we're going to use statistical analysis to ask the question, is there any difference in the performance here? And so basically, we have a null hypothesis that says there is no difference. And the alternate hypothesis says that they performed better when they took action. We're going to use a 2-sample t-test to perform this, and we can conclude from this 2-sample t-test that the inherent haptic feedback from the SRLs, superlimbs, is sufficient to allow the wearer to close the loop and control the force output of the superlimbs. So this is really important, because this means that essentially just through the inherent haptic feedback that they are getting, they can actually realistically control the force output of the superlimb, which means we can use it for tasks like standing assistance. We can also look at the kind of broader aggregated data, so that's shown here. The violin plots are essentially probably the density function of the data. It's just more informative, so we're going to use those. And we can measure their performance, as I said, by control accuracy. So this is the RMS error, and then as well as command effort, which is an integration of their command inputs. We also can look at the visual accuracy, and so that's essentially what percent of the time did they get the letter correctly. So every single time they saw a white letter, if they hit the button, that counts as a 1. If they missed it, that counts as a 0. And you can see this person that on average they got roughly 97% of the letters correct in that particular condition. We're first going to ask the question with this data, does the addition of a simultaneous vision task cause performance degradation on the haptic task? And the way we're going to do this is we're going to compare the condition where they only had to do the haptic task with the condition where we added the vision task and they had to do both simultaneously. We're going to use a repeated measures multivariate ANOVA, and based upon this statistical analysis, we find that we cannot reject the null hypothesis. And so we can kind of conclude is there's no evidence that there's a difference in how people performed when we added this visual task. We can ask the same question kind of in reverse, which is, did the addition of a simultaneous haptic task cause a performance degradation on the vision task? And we're going to use a one-tailed matched pair t-test to ask this question, and we find that there is evidence that people performed worse when we added this additional haptic task. And so in conclusion, we found evidence that performance degrades on the visual task, but not on the haptic task when performing both simultaneously. So this is important because it says that when we have to manually control the force output of the superlimb, we do find that people do get worse on the vision task, right? And that's not desirable. So how can we kind of address this? One potential idea is to increase the automation of the superlimb. So rather than having the person fully manual control the superlimb, we can have the superlimb perform some actions autonomously. And so we're going to go ahead and do that in this next experiment. This is, I think it's important to understand why we want to supervise the autonomous actions of the superlimb. The reason is because even if you increase the autonomy and you have the superlimb performing actions without the express kind of input from the person, so it does it autonomously, that's what that means. It's very important that we still supervise the actions of these superlimbs, and the reason for that is for safety, essentially. So you have this robotic system, it's mounted on you. If it starts going haywire and you don't notice, it can cause a lot of damage very quickly. So it's very important that we understand what it's doing when it's doing it. But if the person is multitasking, if the person is performing some other task and the superlimb is operating over here, I might not notice. And so the question essentially we're trying to ask with this experiment is the inherent haptic feedback from these superlimbs sufficient for the person to supervise the actions and understand what's happening with the superlimb despite the fact that they're not looking at the superlimb? Their vision may be elsewhere. And we're once again going to do this with 3 conditions. So we're going to have the vision-only condition, the haptic-only condition, and the haptic and vision condition. The haptic task is going to look something like this. So basically, once again, the person is standing in front of a desk. The superlimb is clamped to the table, and the superlimb is going to follow a randomized path that is filled with known features. So these are features that essentially we taught to the subjects such that they could recognize them. And that took roughly 10 to 15 minutes. So the 4 features that exist here, there's a start, which essentially results from the superlimb going from 0 force up to 5 newtons, 0 newtons up to 5 newtons. There's a buzz feature, which is generated by these piezo kind of motors that exist on the superlimb arm. There's an up feature, which goes from roughly 5 newtons up to about 9 newtons and back down. And then finally, there's an end feature, which goes from 5 newtons back to 0 newtons. And what we're going to do is we're going to judge people's performance based upon how quickly they respond to these features. So that's the response time, as well as how accurately they identify these features. So in this particular case, the subject was correctly able to identify each of these features, and they did so relatively quickly. So the gray square is when we say the feature has started, and the red circle is their response. So we went ahead and performed this experiment as well, and this is the aggregated data. So once again, we have the ability to ask the question, did the addition of a simultaneous vision task cause performance degradation in the haptic task? We're going to once again use a repeated measures multivariate ANOVA, and we find that there was no evidence of statistical evidence that there was a difference in how people perform. Obviously, you can see that it does look like people got worse here, but it's not statistically significant. Still important to know. The second question we can ask is, did the addition of a simultaneous haptic task cause performance degradation on the vision task? Once again, we're going to use a one-tailed matched pair t-test, and we find that we cannot reject the null hypothesis. So the conclusion here is that we found no evidence that the performance degrades on either the visual task or the haptic task when performing both tasks simultaneously. this is important, right? We basically wanted to understand, is this inherent haptic feedback sufficient for the person to supervise the autonomous actions of an SRL, despite the fact that they're busy elsewhere with some sort of visual task? And this suggests that at least within the context of this experiment, we might be good to go. So in conclusion, for these kind of two inherent haptic feedback studies, we found evidence that inherent haptic feedback is sufficient to control the force output of the superlimb, though we did note that performance degrades when we asked people to perform multiple tasks simultaneously. And then when we increase the autonomy of the superlimb such that all the person needs to do is supervise the actions of the superlimb, we found that the inherent haptic feedback is sufficient to supervise these autonomous actions, even in the presence of a simultaneous vision task. So that kind of sums up what I wanted to talk about today. The first kind of half of this presentation talked about exploiting the human high degree of freedom, high redundancy of degree of freedom, in order to kind of solve key challenges in the design of and communication with superlimbs. And so we essentially built a reduced-actuator superlimb that we then controlled with force on the fingertips. The second half of this presentation kind of delved a little deeper into scientific issues, and we found evidence that the inherent haptic feedback from these superlimbs allowed us to both manually control the force as well as supervise the autonomous actions of these superlimbs. So thank you so much for listening. I do want to thank all of these people, some of which are here today. Yeah, thanks.
Super quick.
Ideal.
Yeah, we have plenty of time, so we're going to brief you from that.
Excellent, cool.
So, any questions from the floor?
Yeah.
So you talked about like obviously a lot of inherent haptic feedback.
Yeah.
What did you have to consider in like the design of the actual SRL? Like does how you design the SRL impact how the like individual like actually feels like the
That is
robot?
an excellent question, which I failed to mention.
Can you also repeat the question, Jake?
Sure. So Lucas basically asked, are there design considerations in designing the superlimb that can kind of perhaps enhance, if I'm going to put words in your mouth, the feedback from these superlimbs? And so what I wanted to show here is this slide. And so this was talking about the force that was being reflected back on the person. The force that's reflected back on the person is scaled by a relationship between the length of this arm and the length of this structure, this base. And so obviously if you can do some sort of human factor analysis to understand what the preferred amount of feedback is for a person, what's not painful but is definitely noticeable for that particular part of the body, and you can design the superlimb to actually deliver that amount of feedback at that particular point. And so I think that part of what I failed to mention and should have is that these two experiments hopefully point to the need for designing with the inherent haptic feedback in mind.
Now,
Yeah.
Playing up on that. So, I think your experimental results, in a sense, very much encouraging for the use of superlimbs for various purposes, because we attach the limb directly to the body, and then we get the unit feedback from that. That's actually very, kind of unique features, right? But still, I'm not clear. And actually, your result is saying that the vision, very intense visual task versus this haptic feedback tasks can coexist, and not much deterioration, right? But I know we have lots of kind of conflicting reports, and many works are being done.
Yeah.
Some said that sketchpad and haptics and the visions are going to the same place, somewhat interchanging or interfering. And also, you said that Federico's work several times, and the conclusion was that the human could not actually simultaneously control natural arms and robotic limbs at the same time, right? So in some way, you left some questions and still open. But I know, what is your view as to under what conditions visions versus haptic feedback can coexist and then not, not interfering badly, very, work well. Do you have any kind of design guidelines as to what are actually, successful design in exploiting both aspects? Can you comment on that?
I can try. I think the first thing I'd like to mention in relation to your question is that I think Professor Hogan pointed this out to me. Essentially, if you look at somebody who plays the piano and is able to sing at the same time, they're performing this very, very complex task with kind of different notes they have to hit with each of their 10 fingers. They're potentially even singing as well. So they're doing all of these activities simultaneously, but they're doing that on the basis of decades of training, right? The results shown here are like, wear the Superlimb for 10 minutes, let's go, let's take that data. Obviously with practice, I think you would see an increased ability to do both the vision task and the haptic task simultaneously, or control all limbs and your natural limbs simultaneously as well. So I think some of this is to do with practice. In terms of design guidelines for kind of when the haptic task and the vision task can kind of coexist, I think that's gonna. I don't know if I could give you any hard and fast. I think the thing I would say is build it, try it, and then kind of understand where the limitations are. It's important to me though that Superlimbs are kind of useful when you put them on and not after decades and decades of training. And so I think we have to carefully consider kind of like what we can actually use haptic feedback for, not in the context of, oh, they'll get it eventually, but like it should be useful like today.
Just following on from that, so if you look at the forces being generated on the hip, it's probably more appropriate to consider them in terms of pressure, given 40, 50 newtons is not trivial.
Right.
So is there concern, sort of two parts to this, is there concern first of all that that's become somewhat aversive against, obviously there's intervening fabric and so on between the robotic limb and the skin, and secondly, would there be concern in terms of long-term use about sort of adaptation to that continual sensory input that would in fact lead to a decrease in the performance of your ability to control because you're no longer actually attending to it?
I will leave the second question to you. I'm certainly not an expert. The first question, yes. Essentially the question was if we am I worried about the kind of abrasiveness of this haptic feedback? And I think we did an earlier experiment where we focused the feedback on these two metal pads essentially that were on the person, and universally panned. Everybody was like, that's super uncomfortable. Like they all knew what was happening, it was good feedback, but it was really uncomfortable to wear. And so I do think a very important consideration when using these kind of haptic feedbacks and the design of the Superlimb base is the comfort of the person, perhaps above all, right? Because we want them to wear it for a long period of time. So I think it's a question of kind of designing the Superlimb and scaling the force outputs based upon what you expect from the task, such that they're within that comfortable range that the person is gonna not hate immediately. Yeah.
Second part?
Second part, I'm certainly not an expert on whether somebody would eventually adapt and ignore that. So I know if you have like a continual stimulus in like a kind of short period of time, you'll eventually just tune it out. I don't know after like days and weeks and months of using it, if you would start to tune out that stimulus, especially if it was like critical to you performing that task. I imagine if it's somehow critical to you performing it, that's something you're going to continue to pay attention to. Whereas if it's like just noise and you're trying to get rid of it, you might eventually just ignore it.
And then criticality is based on factors. So it's an optimization of those two things.
Yeah.
Great presentation.
Thank you.
This is kind of a basic question. You put up a plot with the finger force sensors.
Mm-hmm.
Could you explain what's meant by negative counts?
Oh yeah, so that's just the projection of that into the subspace S results in just the data skewing negative. It's meaningless, etc. Yeah. Yeah.
Thank you for this presentation. I have a question about design and gender. Almost all of the pictures that you showed were men wearing robots and demonstrating things with robots.
Yeah.
Probably also reflects the dominance of men in the field of mechanical engineering. But you did have one video where there was a woman in it, and I'm curious how engineers like you yourself, or even in your own work, how when you think about the bodies wearing the robot or wearing your Superlimbs and the haptic feedback, and where they work and how big they are and how tall you are, just like things that are different between bodies when the designers are often men, how those considerations went into your work, even switching between you wearing the door opening thing and then a woman wearing it, like what kind of lessons did you learn and things you'd recommend for other engineers?
Sure. So if you were to take a class on this, they would essentially give you a textbook which has all this data, which is like the 5% to 95% female and the 5% to 95% male, and then you consider the population you're going to design for, and you fit within that. In my particular case, you're correct. It was designed to be somewhat unisex, but I do want to highlight like one particular example here. Dan Keurig's work on the top right here. We actually had some kind of considerations about whether this particular superlimb should be on the front of the body or on the back of the body. And he, as well as some other grad students in our lab, actually ended up putting it on the back. And the result of that was because if you're a woman, having this thing on the front kind of pressing against you would be very uncomfortable. And so I think it is something we consider. I don't think it's something we consider enough. In my particular case, because most of these were like kind of quick human subject demonstrations opposed to commercially available products, I was more concerned with like, will it fit me and the like 10 people I'm going to talk to, rather than is it going to fit the 5 to 95% population.
I know that the young lady wearing the Superlimbs on the Halloween days in Tokyo, but that's the only garb to wear. Anyway, going back to that first one.
So one of your perhaps surprising results is the interference or lack of interference between the haptic and the visual task performance. But if I recall correctly, you only looked at success rate, not at the time to make decisions. So did you look at the time required to perform the task, and was there any difference in that measure?
I did look at time to. Too far. I did look at time, and it was here. So you can see that's not the one I want. Sorry about that. It's this middle graph right here, or excuse me, top graph right there, which is the response time to the features. And you can see that there isn't a significant difference. I would personally attribute that to the kind of simplicity of the task. I absolutely agree. I think if it was a more demanding, complex task, you would likely see a slowed response when they were forced to do both simultaneously. But in the particular context of this experiment, we did not see a slowed in response.
And then a technical question. You used analysis of variance, which assumes Gaussian distribution, but all of your little violin plots look highly non-Gaussian. Did you check for whether the distributions fit Gaussian?
I did not.
So what does that say about the validity of your statistical conclusions?
That I need to check and ensure that they are correct. It's probably not as accurate as it should be.
So, I mean, what's your own sense? I mean, statistical significance is always
Great.
nice if you get it, but you have to be careful about how you interpret it. The results that are the most surprising are the non-results.
Yeah.
So in particular, your accuracy with haptic and vision comes out statistically not distinct from haptic only. And I mean, that statistical analysis looks right to me. The error bars are so big. Do you have any idea what's going on? Could that error bar be disguising something like, for example, a temporal performance that changes over time?
It certainly could.
It's relatively big. Do you agree?
I do. I think. So subjectively, I guess I would answer this subjectively, because I agree that the statistical analysis is kind of, it depends on what's happening. But subjectively, talking to the subjects who were performing these tasks, they didn't seem to be under more demand while they were performing both tasks simultaneously than when they were performing only a single task. And I think, again, I'm going to lean on the kind of simplicity of this task to kind of explain that. I think it does, there's certainly possible that there was some sort of learning. We tried to design these tasks in the pilot such that it did not require a significant amount of learning. So it would surprise me if there was a significant amount of learning, but it's possible there was some.
So to follow up on that, a related question would be, and this is beyond the scope of what you've done, could you find a way can you think of how to redesign tasks to find under what circumstances you will get an interference? Because that's really what I'd like to know.
Yeah.
I mean, I drive a car, I talk on the phone, but if you give me too many things to do, I'm going to not be able to manage the car.
Right.
For example, if I text.
Yeah.
So there's a sweet spot, and then there's a part where you kind of don't want to go. How would you find it in this case?
I think you would basically look at what the acceptable performance is on the particular tasks you're interested in. And so if the acceptable performance is that I need to be 90% accuracy or 90% accurate on whatever that task is, based upon whatever metric I'm using, and then you continually just kind of add in tasks until the person fails that metric in some statistically or otherwise meaningful way. And so I think it would be a case-by-case basis, at least for me, in terms of like setting some minimum threshold of performance and then saying how much can I give them before they fail that.
So you think it's an information processing bandwidth consideration rather than resolution of the sensors. So I'm sensing things you're doing to my hips.
Yeah.
You know, I'm not sure how good I am at that, but
It's certainly both. So if you had a task that was only reflecting a significantly smaller amount of force, I think it would eventually fall below some sort of threshold, and you would no longer be able to sense it. Everything above, I think it would be fairly easy to sense. So it's both the information processing bandwidth kind of problem, as well as just like the amount of force that's being, or amount of feedback that's being delivered to the person.
Following up Professor Hogan's questions, and have you? I think you have changed the frequency at which the visual, data are actually changed, right?
Yep.
At the end you picked just one frequency.
Right.
How did you arrive at that frequency? Any chance that you changed that as a preliminary experiment?
Yeah, so we did some pilot experiments as well as an entirely different subject testing experiment where we did vary the visual frequency of the vision task, and we found that kind of similar to how I've been describing, there was essentially like reasonably uniform performance, and then it just dropped off when people were just unable to keep up. I think the other thing we found that as you increased the demand of the visual task, the performance on the haptic task would suffer. And so essentially the demand of the visual task would result in worse performance. For this particular task, we essentially tried to choose something that people would not get right 100% of the time, because we wanted them to be able to degrade and be able to improve. So it was piloted based upon this kind of sweet spot of not too difficult that they're just going to fail everything, but difficult enough that they were imperfect. Yeah.
So a related follow-on question. So your tasks were all essentially decision-making, categorizing tasks. But a lot of tasks that I do are more like continuous motion production or continuous tracking or other things. So it's, again, driving a car, it's not just that I decide whether or not to steer the wheel, I kind of need to keep it in the middle of the lane.
Yeah.
Can you extrapolate how these results that you have might carry over to tasks which have more of a continuous...
So I'd actually point to the first task we looked at, which was the kind of force control of the Superlimb. So this is perhaps more continuous to your point. And we found that when the person had the continuous tasks are essentially more demanding of the person, they require more frequent kind of check-ins. And this frequency of check-ins resulted in that when the person had to perform both at the same time, they got worse on the visual task. And so I think the more often that you have to kind of check in with the car to make sure it's in the lane or whatever, the more likely or the less demanding the rest of the stuff you're doing can be.
Could your data come up with an estimate of what that bandwidth is? So at what sampling rate do I start to have trouble? I mean, you've got continuous
I imagine
resonance.
I could. I'm not quite sure how I'd approach that. I think you would have to look at essentially how often they had a command input and whether that affected the output.
Going back to the multivariate analysis on your haptic tasks. So correct me if I'm wrong, but you have this assumption, or you think that, say, response accuracy and response time are correlated when you do a multivariate analysis? And are they actually correlated, or would it make more sense if you look at, say, a univariate analysis?
Because they are derived from the same data, I imagine they are. And so essentially, the kind of subjective, intuitively, you would imagine that if somebody is forced to respond, they're trying to make sure their response is as quick as possible. As they increase their accuracies, as they decrease response time, their accuracy is also going to decrease because they're trying to respond really, really quickly. Whereas because if they're kind of able to wait a little longer, they're able to better identify the feature because they can kind of look at a time series of data as opposed to an individual point. And based upon that, you would expect that if they wait a little longer, their response time goes up, but their accuracy also goes up. So
Have you checked that?
I have not.
Okay. Right. And just like, no.
Just a question regarding the force control on the fingertips
Yeah.
with respect to the door opening. Why select that given most applications of that with heavier boxes and so on, you're going to have much more difficulty controlling 3 pairs of fingers without being able to make adjustments for slippage, slipping on the floor, slipping out of the fingers and so on. Do you think other parts of the anatomy might be more promising as the control input for that task?
Certainly you could use others. Part of the reason we chose that is because people have very dexterous control over their hands. And so you can make an argument that it takes the least practice essentially to be able to initiate the commands that we're seeking if you use the very well practiced and very well censored fingers. You could absolutely use some other part of the anatomy. I've seen there was a superlimb that was controlled essentially for surgical robotics, and they found that they would basically have the person sit and the superlimb would mirror the position of their foot. And that was very successful because what they basically did is said the foot is not being used in this particular task, and therefore we're going to use that to control the superlimb. I think one of the parts that I failed to mention this particular work is that, you know, despite the fact that we're using our hands for this work, we're still able to use them to kind of control the superlimb. And so it's a different kind of approach where they're essentially looking for some signal that is totally different, whereas we're saying despite the fact that we're using these, we can still use the redundancy within this particular piece of anatomy to control the superlimbs.
So I'm wondering as well, when there's input for the haptic feedback while the vision is going on, are they still using the Xbox controller to like categorize the buzz or the? And I'm wondering if the increased sort of error bar variance performance could have been due to like if a failure mode is more people timing out on making a decision. If so, I know for instance people who would use an Xbox controller quite often, you'll input different buttons without even looking at what you're doing, versus someone who's maybe not as used to using the controller would have to look down and spend time figuring out which button to press. And I wonder if that could lead to a greater variance in performance.
I think you're absolutely correct. The other part of this is we had to essentially map a feature to a specific button, right? And so what we found often was that people would be like, press A, and if A corresponded to the up feature, they would press like B or something, even though they knew it was A, and then you hear this audible like crap, right? I knew it was A, I wanted to press A, I just forgot. One of the things we tried to do to alleviate this problem within our pilot is we used different button combinations. Often, and ultimately what we found is if you kind of divide the controller so that they use their right hand to interact with the visual task, and they use their left hand to interact with the haptic task, that people generally with a little bit of practice could get pretty good at it. So we did try to account for that, but you're absolutely right. If somebody was super comfortable with it, they'd be a lot better. Yeah.
Okay, so let's thank the guest speaker.